Hey there, welcome back to Short Takes 331. Today we're going to talk about the Fourier series and its first concepts. So this is something I've been wanting to do for a while. I don't think this is usually taught this way, so let's jump right in. So you know about Taylor series, presumably. So you know that under certain conditions you can take a function and expand it in powers of these monomials, x minus x0, x minus x0 squared, and so on, with some reference point x0. And so you will have coefficients a0, a1, a2, and so on, which are given by derivatives, of course. And you can say then that these are the coordinates of f of x in the basis x given by 1, which is this guy here, x minus x0, s minus x0 squared, and so on and so forth, in principle all the way to infinity. Now, different points, x0, different reference points, will give you different coordinates, because a0 depends on the function evaluated at x0, a1 depends on the derivative of the function evaluated at x0, a2 on a second derivative divided by 2 factorial, and so on and so forth. This is, of course, what you learn about the Taylor expansion, and it's a local expansion around a specific point. So let's look at an example, even though I think most of you already know about this. So this is our function f of x is e to the minus x squared. It's shown here in blue. So it goes from here to here in blue. Now, if you do a 0th order expansion, then the function evaluated at 0 is, of course, 1, and it just gives you this solid line. And it's really a terrible approximation to this blue curve. So this orange line is really a very bad approximation. It only really looks like the function around the 0 point, which is, of course, what it's supposed to do. But by itself, it's a very bad approximation. And so you go ahead and you include the next order, the next non-zero order, and that's x squared. And so you get 1 minus x squared, and so you get this parabola here in green. And you can go ahead and include one more order, x to the 4th, and then you get this other curve. And then you can keep going and add one more order and obtain this this violet curve here, and so on and so forth. And so if you were to calculate the coefficient, you'll find that because we chose this point x0 equal to 0 as a reference point, you find that f of x0 is 1, f prime of x0, this should say f prime of x0 is 0, f double prime of x0 is 2, and so on and so forth, and that's why you obtain these various coefficients. And that tells us simply that the coordinates we referred to above are a0, a1, a2, all the way to infinity, equal to 1, 0, 2, 0, something else, 0, and so on. So all the odd ones are 0 when you choose 0 as a reference point, simply because of the symmetry of our function. Now, the Fourier series really you should regard as just another basis. Instead of being the basis of monomials, which here are powers of x, and up here we wrote more generally as powers of x minus x0, so you really want to see the Fourier series as just another basis where the coefficients or the coordinates are a, k, b, k. That's typically what they're called. And the basis is given by 1 cosine pi x over L, sine pi x over L, cosine 2 pi x over L, sine 2 pi x over L, and so on, where our function is defined in some interval minus L to L. Now, of course, these functions, cosine k pi over L and sine k pi over L, are unable to reproduce any function that is not periodic outside of this interval, and so we just specify it on this interval. But presumably your function is some kind of signal that repeats itself outside of this interval, and so if it goes up and down inside this interval, then it does the same on the next interval over, and between L and I guess 3L, and between minus L and minus 3L, and so on and so forth, in all directions, all the way to infinite values of x. It continues repeating itself, and that's, of course, the only thing that these functions can do. The sine and the cosine will continue to oscillate up and down, and it will not give you anything different. So in this case, instead of doing derivatives, we have to do integrals. This is a different type of expansion in that sense. It's more of a global expansion, and the coefficients are calculated in this way. So a0 is 1 over L, integral between minus LL of f of x dx, so it's sort of an average of the function. If you include this 2 here and you put it down here, you see that it's an average. It's a kind of average. And by the way, this 2 here is nothing other than convention, so that we can write this formula in this way, and the following formulas in a very similar way without any extra factors of 2 or anything. So ak then is 1 over L, and the integral between minus L and L, f of x, cosine of k pi x over L, and bk is similar but with the sine instead of the cosine. And if this looks like an inner product between f and the cosine divided by L, and same here, then it's because it is. It's really an inner product of our function with the functions of the basis, with the vectors in the basis. I encourage you to go and check out the video on inner product that I did a few videos ago. I don't remember exactly which one it is, but it's a few videos ago. So as an example, let's take another function that is a little bit like the Gaussian that we analyzed before, but now is e to the minus x squared cosine of 3x. So we add some oscillations to this. And we obtain this. If we calculate these coefficients, we go ahead and calculate these coefficients, we obtain this. We obtain some constant, which is of course our a0 over 2. We obtain cosine x, cosine 2x, and so on. And in this case, I chose the interval to be between minus pi and pi. So I chose L to be pi. You can choose L to be whatever suits your case, whatever it is that you're studying. So here I chose it to be pi so that I could simplify the expressions here when playing with this example. But here what you get is as follows. So our function here would be in blue, and you cannot really see it because it's obscured behind the cosine to the cosine of 6x term, or not just the term, but the expansion all the way to cosine of 6x is basically indistinguishable from our function f of x. So imagine that the orange curve then is completely covering the blue curve, which is the exact function. And you see that if we were to look at this light orange curve is up to cosine of 2x, so up to this one that is written here, then you can add one more term and you obtain the green curve, and it starts to look like the other one. And then when you get to order 6, then it's basically indistinguishable on this plot. You can see a little bit of blue in the background there and there, but it's basically a pretty good approximation. You also notice here that there's no sine of x, and this is because e to the minus x squared cosine 3x, our function, is an even function. And when your function is even, then all the bk's will be 0. And this is also true vice versa. If your function is odd, then all the a's are going to be 0 and all the b's are going to, in general, remain. It may be that some of them vanish by chance, but typically the b's will be non-zero, and you can prove that the a's would have to be 0 if your function is odd. So here again, here is even, and so the bk's have to be 0 for all values of k. And the coefficients are, as I wrote here, a0 over 2 is just this number here, 0.02973. a1 is this other coefficient, and a2 is this 0.22024. So why would you use the Fourier basis? And by the way, we will continue seeing examples in upcoming videos. But why would you do this? Why would you choose to do something like this? It looks complicated. It looks like you have to go to order 6 to get something nice. Why not use a Taylor series where you can calculate the coefficients by taking derivatives, which is something we all can do more or less mechanically, whereas these integrals look more complicated. And the answer to that is really that is convenience and physical reasons. So in this case, it may not look like it's convenient, but it could be. It could be convenient because there's physics behind this. And the reason usually physics appears in this when you use Fourier basis is that the cosine of kx is a linear combination of e to the ikx and e to the minus ikx. So it's a linear combination of two complex exponentials. And the same for the sine. The sine of kx is a linear combination of complex exponentials. So the whole Fourier series really entirely relies on this plane wave, on this e to the plus minus ikx type of object, this complex exponential. And turns out this is an eigenfunction of minus the second derivative, which is an operator that we studied in previous videos. We studied it with hard wall boundary conditions, and so the sine and the cosine appear naturally there. But if you study it in all of space or with periodic boundary conditions, then you'll have that this is the object that appears naturally. Our Fourier basis then, as written here, it's an eigenfunction of this second derivative operator with a minus sign with periodic boundary conditions, not with hard wall boundary conditions. So with hard wall boundary conditions, it's you obtain the cosines disappear from the basis, you obtain just the sines. But with periodic boundary conditions such that the function at one endpoint is equal to the function at the other endpoint, then these are the functions. And so that's why we end up using this basis a lot of the time, because we're interested in this second derivative operator with a minus sign, because what we have is either a Schrödinger equation or a diffusion equation or some kind of wave equation where this really plays a major role. And so it's very natural for us to use the Fourier basis. This is ultimately the reason behind us using this basis as a way to analyze a signal, or as a way to write down the solution of a problem, or as a way to make a problem simpler in some way. And we will see applications of that in upcoming videos once again. And we actually saw sort of under wraps an application of this when we diagonalized a differential operator on the lattice using these types of plane waves. So I think I will stop here. If you enjoy the videos, as always, please like and subscribe. If you are looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. And that is all. Until next time.